Hobart School of Welding Technology presents Training in Gas Tungsten Arc Welding Pipe and Tubing. Topic number 18, Lecture Discussion. Stainless Steel Pipe Welding. Objective: to develop an understanding of the factors which affect the welding of stainless steel pipe and tube. Stainless steels are iron base alloys which have an excellent resistance to corrosion. These steels do not rust and resist attack from most liquids, gases, and chemicals. Stainless steels contain chromium in an amount from 11 to 30%, which imparts the corrosion-resistant properties to the metal. When exposed to oxygen in the air, the surface of stainless steel develops a thin film of chromium oxide. This film acts as a further barrier to oxidation, rust, and corrosion. Stainless steels are available in three major categories based on microstructure: austenitic, martensitic, and ferritic. The individual types of stainless steels within each group are classified by the American Iron and Steel Institute with a 3-digit number. The martensitic and ferritic types are classified in the 400 series. These are called the straight chromes, since these steels contain only chromium, or chromium with small amounts of other alloys. For instance, a 410 stainless has a martensitic structure, while a 430 has a ferritic structure. The austenitic type stainless steels are designated with a 300 series number. These are called the chrome-nickel stainless steels because of the addition of nickel as an alloying element. Some examples of the austenitic steels are 304, 308, 310, 347, and so on. Sometimes an L is placed after the 3-digit designation to indicate a low carbon content. For instance, a 316L would be an austenitic stainless steel with a carbon content of 0.03% maximum. We will restrict our discussion of stainless steels to the austenitic group, since this series has the best weldability and is the most common type welded. The selection of filler metals for austenitic stainless steels is based on the chemical composition of the base metal. Filler metals used with the gas tungsten arc process are usually provided in pre-cut lengths or in coils. The filler metal is bare and solid, which eliminates the problem of moisture pickup as compared to covered electrodes. These filler metals should be kept in a clean storage area to prevent contamination by dirt or other foreign materials. Bare filler rods are classified by the American Welding Society similar to the AISI classification of base metals. For example, an ER310 is a stainless steel electrode or rod, indicated by the letters E and R. The 310 indicates that the filler rod has a chemical composition similar to a 310 base metal in the AISI classification. Shielded metal arc welding electrodes for stainless steels are classified similar to bare filler rods. However, shielded metal arc electrodes require an electrode coating to prevent weld contamination. Two types of coatings are normally used on stainless steel covered electrodes. One is referred to as a lime type and has a suffix designation of 15. The other type contains titania, or titania dioxide, and is referred to as a titania coating with a designation of 16. The lime type electrodes are normally used with direct current electrode positive. The titania types can be used with direct current electrode positive or alternating current. Some types of titania electrodes can be used with direct current electrode negative, where lighter penetration is desired. Both lime and titania type electrode coatings are the low hydrogen type, which are susceptible to moisture pickup. Once the electrodes are removed from their sealed containers, they should be stored in a warm, dry environment. Open electrodes should be stored in a heated oven at an approximate temperature range of 250 to 450 degrees Fahrenheit. Electrodes which have picked up an excessive amount of moisture can cause porosity, flaking of the coating, and an erratic arc. Damp electrodes can be reconditioned by heating in a special oven. The oven is set at a specific temperature depending on the type of electrode being conditioned. One problem which can occur when welding austenitic stainless steels is carbide precipitation. This occurs when the steel is held at 900 to 1600 degrees Fahrenheit for prolonged periods of time. In this situation, carbon combines with chromium to form chromium carbides, which reduce the corrosion-resistant properties of stainless steels. This problem can be reduced through proper selection of filler metals and interpass control. Selection of a low-carbon filler material can reduce the problem. For instance, an ER308L filler metal contains a carbon content of 0.03%. This adds only a small amount of carbon to the weld, reducing the amount of carbon that can combine with the chromium to form carbides. Another method is to use a filler metal containing stabilizing elements, such as columbium, titanium, or tantalum. These elements tie up the carbon to prevent the carbon from combining with chromium. The maximum temperature of the base metal between passes can be controlled to prevent holding the temperature at a point where carbide precipitation can occur. After each pass, the welder must wait, if necessary, until the temperature drops below the maximum interpass temperature prior to depositing the next pass. The techniques for welding stainless steel pipe are similar to those used for carbon steel pipe, except for certain special considerations. It is always important to keep the weld joint clean from all contaminants, including paint, scale, rust, and dirt. Clean white gloves should be worn while preparing joints. In addition, a stainless steel wire brush should be used to clean the welded surfaces in order to prevent contaminants from being deposited in the weld. A carbon steel brush should not be used since it may introduce contaminants into the weld metal. The tack welding operation for stainless steel pipe is more complicated than for carbon steel, since the inside of the pipe must be purged to replace the oxidizing atmosphere with inert gas. The inert gas protects the root of the weld and adjacent edges of the joint from oxidation. Argon is the most common gas used for purging because it is inert and relatively inexpensive. However, argon-helium mixtures or nitrogen are sometimes used. To tack weld a pipe joint, small spacers can be placed in the joint to provide the proper root opening. The joint is then taped to prevent the purging gas from escaping through the root opening. Purging caps are placed in each end of the pipe joint. These caps can be made of steel, wood, plastic, or even cardboard. Holes are placed in each cap. The hole on one end receives purging gas from a cylinder or other source. A hole is located in the other cap to allow the air to escape as the purging gas replaces it. Since argon is heavier than air, the exhaust hole should be located higher to prevent. A window is placed in one of the caps to allow visibility of the root of the joint. Water-soluble dams are also used to contain the purging gas. They are fastened to the inside of the pipe and then dissolved with water after welding. The purging gas is allowed to flow at a given rate for a specific time prior to depositing the first tack weld. The flow rate and purge time depend on the maximum oxygen level permitted and the size of the pipe system. The pre-purge time depends on the gas flow rate being used. The higher the flow rate, the less pre-purge time is required. However, the flow rate should not be set so high that a turbulent flow is caused, which creates a mix of trapped air and purging gas. Once the pipe has been pre-purged for the desired length of time, the tack welds are deposited. Sections of tape are removed, and the tack welds are deposited at each quarter of the pipe. The tacks are then wire brushed and the tape replaced. Before depositing the root pass, the purging gas flow rate is reduced to eliminate pressure buildup in the pipe. Excessive pressure on the inside of the pipe can result in internal root concavity. When welding with consumable inserts, flow rates in the neighborhood of 10 to 15 cubic feet per hour are normally sufficient. If open root joints are being welded, then flow rates of 15 to 20 cubic feet per hour are normally required. The welding of stainless steel pipe is similar to the techniques used for carbon steel pipe. When depositing a gas tungsten arc root pass, the tape is removed from the joint as welding progresses up the joint. Where high-quality weld results are required, a high-frequency start may be necessary to avoid crack-sensitive areas caused by scratch starting. A copper starting block may also be used for the same purpose. Each pass should be carefully cleaned with a stainless steel wire brush. The shielded metal arc welding process is commonly used for fill and cap passes on stainless steel pipe. Stainless steel covered electrodes do not have as deep a penetrating characteristic as do most mild and low alloy steel electrodes. This sometimes makes it difficult to attain adequate fusion. Also, characteristic of stainless steel electrodes is their greater fluidity, making puddle control difficult. Because of these factors, it is necessary to keep the arc directed onto the leading edge of the puddle by using a slightly faster travel speed. Faster speeds also produce smaller weld beads, which are easier to control. Each successive bead is thoroughly cleaned to remove slag. Slag left on the weld bead can result in slag inclusions when subsequent passes are made. The techniques for welding carbon steel pipe can be applied directly to stainless steel pipe, providing that a knowledge of special considerations is developed. With the shielded metal arc process, a greater skill level is usually required due to puddle characteristics.